Today we're going to continue on with phase 2 of trigonometric substitution, integrating the theta integral. The theta integral will come in two varieties that we have to deal with. The odd powers of secant and the even powers of cosine. We're going to use the strategy of double angle identities to do our even powers of cosine. You can see parts in play if you go into section 7.2, example 6. Your textbook will integrate cosine squared using parts and a little bit of the trickery that we did last time. So that's kind of cool. I recommend you check it out. What we're going to do is use a double angle identity to help us integrate even powers of cosine. So for example, if we want to integrate cosine squared of theta to theta, we're just going to replace it with the double angle identity. Cosine squared is 1/2 plus 1/2 cosine of 2 theta. Replace your cosine squared with the double angle identity involving cosine squared and cosine. The reason is integrating cosine with the 2 as an exponent is wildly inconvenient. Integrating cosine with the 2 as a coefficient in the argument is borderline trivial. So the integral of 1/2 d theta is just a 1/2 theta. The integral of cosine of 2 theta is sine of 1/2 sine of 2 theta. So we'll have a 1/4 sine of 2 theta plus c. Looking ahead to phase 3 and also looking back to example 6 where this was done by parts, notice that we ended up with a sine of 2 theta in this version. Looking ahead to phase 3, when we're going to have to take theta back to x, it's inconvenient to have a sine of 2 theta, so we're going to use a double angle identity to get out of that, just to rewrite that portion. So looking ahead to phase 3, replace your sine of 2 theta with 2 sine theta cosine theta. Use a double angle identity. So we're going to replace our sine of 2 theta with 2 sine theta cosine theta. And so we'll end up with a 1/2 theta plus, I spelled plus wrong. A 1/2 theta plus a 1/2 sine theta cosine theta. Double angle in, double angle out. Once we learn the trick, it's pretty simple moving forward. So we'll do like we did with the the odd powers of secant. We'll go to the next even power of cosine. If the next power of cosine, cosine cubed, we can just make a substitution W equals psi, save one of the cosines to be the dW. Life is pretty easy when we have odd powers of cosines and sines. It's the even ones that we have to watch out for. So our strategy is going to be to replace cosine squared with our double angle identity. So when we look at cosine to the fourth, we're going to read this as cosine squared squared. So we're going to read cosine squared theta all squared. I'm going to replace cosine squared with our double angle identity, a half plus a half cosine of 2 theta. But then I'm going to have to square this before we integrate. This is going to result in another cosine squared. Once I multiply this out, I'm going to end up with another cosine squared. But we're going to do the same thing. The strategy is to replace cosine squared with the double angle identity. So let's see what happens here. When I multiply all this out, I get a 1/4 plus a fourth times 2, so a half cosine of 2 theta. This is what we wanted to happen, plus a 1/4 cosine squared of 2 theta. This is what we did not want. So once I multiply all this out again, I get a cosine squared show up again. But our strategy is the same. Replace the cosine squared with a double angle identity. We're just taking the cosine. Originally, we have cosine squared theta is a half plus a half cosine of 2 theta. So if I double up the theta in the cosine squared, I just double up the 2 theta in the cosine. So we've got two fractions running around here. We got this 1/4, we got two constants, the 1/4 and then this 1/8 right here. So 2/8 plus 1/8 is 3/8. And then I got a 1/2 cosine of 2 theta plus a fourth of a half or 1/8 of a cosine of 4 theta, d theta. And so we've accomplished what we want to accomplish. We got rid of the cosine squareds and replaced them with a cosine of n theta, cosine of 2k theta, which, as previously noted, is borderline trivial to integrate. Now we can just integrate our 3 terms. And we have our antiderivative in theta. If all we had to do was integrate cosine of the fourth theta using the double angle identities, this would be where we are done. If we are thinking about this in the context of trigonometric substitution, and we're going to want to get out of theta back to x, if we're going to want to undo the substitution that we opened with, we're going to have to get the sine of 2 theta and the sine of 4 theta down to sines and cosines of just theta, because that's what we're going to have available. So we're going to once again double angle out. So I'm going to replace my sine of 2 theta and my sine of 4 theta with the double angle identity for sine. That needs more space. Maybe. So my sine of 2 theta is going to be 2 sine theta cosine theta. My sine of 4 theta, I'm going to use the double angle identity, but instead of being 2 sine theta cosine theta, since it's a sine of 4 theta, it's going to be 2 sine 2 theta cosine 2 theta. And if you're thinking, wow, now we've got sine of 2 theta and cosine of 2 theta still. So if we want to go back all the way to theta, then we're just going to double angle identity those. So let's take care of these first two. We got a 3/8 theta. Then I got a 1/2 sine theta cosine theta. Plus a 1/16 sine of 2 theta cosine of 2 theta. Plus C. And then we just double angle identity yet again on our sine of 2 theta and our cosine of 2 theta. For our cosine of 2 theta, we could just use the same expression that we had before. We had cosine squared is 1/2 plus 1/2 cosine of 2 theta. I don't think I wrote that down anywhere. But we had cosine squared theta is a 1/2 plus a 1/2 cosine of 2 theta. So if we solve this for cosine of 2 theta, multiply by 2 and then subtract 1. It's going to be 2 cosine squared theta minus 1. At this point, you might be thinking, dude, we went through all this trouble to get rid of the cosine squared. Why are we putting it back now? The reason that we got rid of the cosine squared is that it was inconvenient when we were integrating. We are done integrating. It's fine if it shows up again. Having a cosine squared when we're going back to our x antiderivative, or when we're going forward to our x antiderivative, that's not as critical. It's okay to have it now because we're done with the integration part. Now this is a little bit messy because I noticed that I have a sine theta cosine theta term here and a sine theta cosine theta term here. So we should combine those. And then this middle term here is going to give us a sine theta cosine cube theta. But it's okay to have powers of theta because we're just going back to the x variable. So, excuse me, over here, we're going to have a 1/8 sine theta cosine, a 1/4. So the distributive property here will give us a 1/4 sine theta cosine cubed. This will still be 3/8 theta. And I have this half sine theta cosine theta minus an 1/8 sine theta cosine theta. So a 1/2 minus 1/8. Yeah, 1/2 here minus 1/8. So 4/8 minus 1/8 is 3/8. And then all this is an integral, so plus c. But with an eye of trigonometric substitution going back to the variable x, we will want all of our thetas to be expressed as single thetas in the arguments. So we replace the 2 thetas with double angle identities. Oh, 3/8. 3/8 plus 3/8, yes. Thank you. At this point, you might be thinking, this seems like we are pretty deep in the weeds right now, but that's only because we are pretty deep in the weeds right now. And you're starting to wonder, man, when am I going to have to do this in my life? And the answer is not anymore. You just did. All you have to do is remember the integral for cosine to the 4th, and now you are done with doing the integral from cosine to the 4th. You know what it is now. 3/8 theta plus 3/8 sine theta cosine theta plus 1/4 sine theta cosine cubed theta. Here's the other reason that you might want to do this exercise. I'll go a little further on this exercise. If you really want to be trained on this, do the same thing for cosine to the 6th. That would just be the next one up. You're going to have some fraction. There's going to be a theta. There's going to be a sine theta cosine theta. There's going to be a sine theta sine cube theta. There's going to be a sine theta. Anyone going to guess what the next one is going to have? There's a theta, sine theta, cosine theta. That's what we had with cosine squared, first level. cosine to the fourth, second level, theta, sine theta, sine theta, cosine cube theta. What are we going to have? How many terms are there going to be when we do cosine to the sixth? We're going to have to do it unless you can tell me how many terms there are and what form those terms are going to take. I don't care about the coefficients. How many terms are there going to be? What happened when we went up one level from cosine squared to cosine fourth? How many more terms did we get? Cosine squared, oops, that's not it. Cosine squared had two terms, a theta and a sine theta, cosine theta. Cosine of the fourth had three terms, theta, sine theta, cosine theta. Like before, the new kid on the block is sine theta, cosine cube. Speculate. What happens if we go up to the sine to the sixth? How many terms are there going to be? We went up one. A reasonable guess would be to go up one more term. Going up two terms, that would be also a reasonable thing. But we want to think as small as possible. I bet going to a cosine of the sixth will add one more term. What form will that term take? Do we have enough of a pattern? This is what I would speculate. This is just my recommendation. If you want to try this as far as your speculation goes. I would suspect that we're going to get, since we went from 4 to 2 to 4, dropped us this other term on here. We had a constant, our third term had a sine theta, cosine cube theta. So I would speculate that we get another term like that. Because we think back to what happened when we were integrating higher odd powers of secant. We got the previous stuff with this new term that was kind of a variation on the old term. So I would speculate, I'm going to speculate that another term shows up with some constants that we'd have to work out. What do you want to speculate on this form? Sine theta, cosine to the fifth. That seems to be kind of what's going on. We start off with a theta, sine 1, cosine 1. Then we had sine to the first, cosine to the third. So maybe that sine is just going to stick around. That's reasonable because of where this comes from, right? These double angle identities. So a good speculation would be, is it sine theta, cosine to the fifth theta? It's always 3. I can't just do 2. This seems like a good speculation about what the power should be, about what the form of the term should be. Right. Wolfram alpha leaves it as the 2x's and the 4x's and the 6x's. But that's okay. Looks like we're going to have to do it by hand. So let's get started. I'm just kidding. I'm not going to do that right now. Now you're thinking, oh no, who's going to assign it? No, I'm not. Because remember, every time y'all have to do a problem, every time I ask y'all to do a problem, especially one that's going to be like this, I have to do that problem 40 times. I know what the answer is supposed to be, but then I have to do the problem 40 times because I have to read all of your answers. Then I got to figure out if it's wrong, where you went wrong, and then let you know. And then I've got to do the problem over again, right? So even though I fully encourage it, would be a great exercise to do cosine of the sixth, I recognize that you might not have time to do such an activity. We just don't have time to go to the gym all the time, right? This would be good calculus gym. Actually, that's not so much calculus gym, it's more like algebra gym and trigonometry gym. Any questions? Oops. Trigonometric substitution, part 3. Phase 1, the substitution, that's the 3 cases where you trade your quadratic form with a Pythagorean identity to get your theta integral. Phase 2, you integrate it. Odd powers of cosine, odd powers of secant, even powers of cosine. Dealt with those. Remember, this integration should not be substitution. If it is substitution, go back to your f of x integral and do the substitution there, not the trigonometric substitution. If I write a quiz on trigonometric substitution, there will be 3 problems. One of them is not a trig sub problem. Even though I say that now, I can write it down in the instructions for the quiz. The second problem is not a trig sub. It'd be like a x times the square root of 9 minus x squared. Someone's going to do trig sub on it. And they go, wow, why do you want to do so much work? So we do the integrate part. We've talked about that. The 2 things that have come up in the integrate phase are the products of powers trig functions that are not substitutions. Now we know how to deal with those 2 cases. We can go to the unsub part. I used to call this go back to your x, but I don't want to encourage people to do that. It's a bad thing to do. They're an x for a reason. So let's just call it unsubstitute. Go from our theta antiderivative to the one that we want, the x antiderivative. So to go back to the x, to trade our theta in for an x. It all starts from our initial substitution. So if we had something like a squared minus x squared, then we made the substitution x equals a times the sine of theta. The first stop on the unsubstitute train is to solve for sine. Sine of theta is x over a. Sine of theta is x over a. The easiest place to go after this is just solve this for theta with the sine inverse. We saw that that happened in our cosine squared. One of the terms was a half times theta. So one of the things that might show up in our integration or in our theta antiderivative is just theta itself. So if we get a theta, we can just replace theta with sine inverse of x over a. Now, if you also remember, in our cosine squared, we had sine theta and cosine theta. If we see sine theta, we can just replace that with x over a. What we are 100% not going to do is write cosine of sine inverse of x over a. That is trash. I don't know, I'm sure there are some Cal 2 teachers that are out there that are okay with that, but that is trash. You will absolutely not do that in this classroom. You will not be writing cosine theta or cosine of sine inverse of x over a. Now I realize my disdain for this form is just as ridiculous as other instructors' disdain for me saying that this is ridiculous. We are both being 100% ridiculous. So if you find someone that is cool with this, I think they're crazy. I think there's something wrong with them. They think I'm too pedantic. We're both being assholes. So in this room, you will not do this. Your job as a student is not to be right. Your job as a student is to assuage the fucking egos of your student instructors. I'm just kidding. Let's not be too ridiculous. Here's what we are going to do. We're going to do this, not because I said so, but because it's cool to do this anyway. Look at this, sine theta is x over a. We're going to use the fact that sine is opposite over hypotenuse. And I'm going to draw a triangle with x as opposite and a as hypotenuse. It's much cooler if you do it this way anyway. So if you want to do it like this, okay, that's fine. Some people will be like, oh yeah, that's fine, just do it that way. But if you want to be cool, we're going to sign opposite x hypotenuse a. So this other side is the thing that probably made you do the trig substitution in the first place. Square root of a squared minus x squared. So instead of writing the stupid cosine of sine inverse of x over a, it's just fine. I'll always make fun of that. I don't know why. I'm just a jerk. You're going to have cosine of theta, and you're going to write it as adjacent over hypotenuse. Then you will be cool. But you also don't get to be a dick about this one. Like when you're trying to be cool about something, you have to not like try to like lord it over people. Just be like, oh no, this is what I do instead. So if, for example, we had some hypothetical stuff happen and we ended up with, let's say, I don't know, a 1/2 theta plus a 1/2 sine theta cosine theta plus c. then undoing our sines and cosines to go to x's, theta can just be the sine inverse. One half sine inverse of x over a. Our sine theta will be x over a. And our cosine theta will be square root of a squared minus x squared over a. Then we would clean this up. We would probably put the x square root of a squared minus x squared over to a squared. And that would be our x antiderivative. That would be going from our theta antiderivative to our x antiderivative. So this is how we undo the substitution that we made in the beginning. We rewrite our original substitution, then draw a triangle to get the other function. If we had done a trig substitution that had a squared plus x squared, and we did the substitution x equals a tangent theta, then our answer, our antiderivative in theta will involve theta, tangent, and secant. And when we do this, we ended up with a bunch of secants, and then the secant led to a bunch of tangents and secants. So any tangent of theta we can write as x over a. We can solve this for theta with a tangent inverse. We are still not going to write something like secant of tangent inverse of x over a. I still think that looks like trash, so we're not going to do it. I'm going to use my original substitution. Tangent of theta is x over a. Read x as opposite and a as adjacent. Tangent is opposite over adjacent. And so our hypotenuse is the square root of a squared plus x squared, the square root of the quadratic that put us in this situation in the first place. And we can use that to write secant. Secant of theta is hypotenuse over adjacent. So if we had done some trigonometric substitution and ended up with a theta antiderivative of natural log of absolute value of secant theta plus tangent theta plus c, then we would go in and replace secant theta with our expression in x. And replace our tangent theta with an expression in x. Then when you look it up on Wolfram alpha, you'll be like, oh, whoa, what happened to all the denominator of A? My recommendation is you take a moment, take some time between now and tomorrow and figure out what happened to the A. Why did I do this? Because if I ask this question on some quiz or test, and you just end up down here, I will say, oh no, those both need to be divided by A. And your argument to me is like, oh, no, we don't need those. Your argument to me can't be like, oh, well, Wolfram alpha said I don't need the A. I didn't need to divide by the 3 there. You have to tell me why. So let's just take care of that now and tell me why we don't have the divided by A in this last expression. How can I get away with just getting rid of dividing by this constant A? Tell me why A is not in the denominator. Tell me why. All right, well, that's for another day. That's going to be it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. And find out what happened to this A.